Welcome back, Chemistry 30. This is booklet 16.4, Calculating Enthalpy Change. It corresponds to page 506 to 512 of the text. And here we'll be looking at Hess's law and standard enthalpy heats of formation. Using Hess's law of summation of enthalpy of a reaction to calculate the enthalpy change of a reaction. Explain the basis for the table of standard enthalpies. Calculate the enthalpy of a reaction using a thermochemical equation. Determine the enthalpy change of a reaction for reaction using standard enthalpy data and using tables, graphs, etc. So, of course, we can't experimentally determine all enthalpies of a certain reaction because they may be difficult to do or dangerous to do. So that's where we come with the idea of, okay, hopefully some of these have been experimentally done already and we can go from there. Which brings us to Hess's law. Now, it won't make too much sense at this point, but once we go through a few examples, it hopefully will. So Hess's law suggests that if you can add two or more thermochemical equations to produce a final equation for a reaction, then adding up the enthalpies associated with those give you the enthalpy of the reaction itself. Okay, so with a question like this, I would give you a question suggesting what is the enthalpy involved in this particular reaction, given that you have two or more reactions to work with, whose enthalpies are known. So for example, number 3 here, if I wanted to figure out the enthalpy involved with this, 2 sulfur plus reaction yielding 2 sulfur trioxide, what would that enthalpy be if I know this reaction involving sulfur dioxide and this reaction involving sulfur trioxide? Okay, so Hess's law suggests that if I can manipulate these equations and when I add them up, if I can get this reaction, then adding up the enthalpies will be the enthalpy for that reaction. So the key thing here is to manipulate these two to make them look like this. So that involves looking at compounds in the original reaction. Usually skip oxygen because a lot of equations involve oxygen. It's too difficult to try to manipulate that. But the other compounds we certainly can. So if I look here, I have 2 sulfurs. And if I look in these other reactions here, there's sulfur right there by itself. So I found it. I need for it to be on the left-hand side of the equation, and it is. It's a reactant, so that's good. But I need 2 of them. 2 moles, or 2 elements, 2 atoms. So in order to get that, I'm going to have to double that, multiply by 2. And if I multiply that by 2, everything in that reaction, including the enthalpy, will have to be doubled as well. Okay, so that's the manipulation I'm going to do with this first green equation you see here. Excuse me. Looking for SO3. It's in the second reaction. I need 2 molecules of it. I got 2, but I need for it to be on the right. It's on the left. So what I can do for that is I can force it to go in the product by imagining it as being flipped or reversed. But it was an endothermic reaction. If I flip it or reverse it to have these being reactants and this being a product, it'll become an exothermic reaction. So the step there will be to reverse it. Okay? So if I do those 2 manipulations here, so first we'll multiply this equation by 2. So if I do that, I'll get 2 S's, 2 O2s, 2 SO2, and negative 294 multiplied by 2, negative 588. And that second equation, reversing it, so these are the reactants. There you see them. And the 2SO3 will be a product, so I need for it to be on the product side. The positive 198 changes to a negative 198. So there I have those equations manipulated. And we can see here we can cancel some things out. If we treat this as 2 mini reactions in an overall one, 2 SO2s are produced here, then 2 SO2s are used as reactants here. So if they're on opposite sides, and if they're equivalent, they can be canceled out. And interestingly enough, we're left with 2S, 2 oxygen, 1 oxygen, together make 3 oxygen, yields 2SO3. 2SO3. So that's what I want it to end up with. It's almost like you have the answer to the question, so that'll help you out. And then Hess's law says that if I can manipulate equations and sum them up so that they become the final reaction I want, to find out the enthalpy of that overall reaction, just add up the enthalpies of the corresponding reactions I manipulated. So negative 588 and negative 198, negative 786. Okay, so there you have it. That's basically how you do it. And we'll do quite a few examples here. So if you're still not quite grasping this, hopefully you will. You have to watch this video one more time or 2 more times. If we look at a graph that illustrates what we did here, we can think of this overall reaction as being made up of 2 smaller reactions. The 2S plus 2O2 yielding 2SO2. 2S plus 2O2 yielding 2SO2. Involves the release of 588. Release of 588. Then from there, the 2SO2 combines with an oxygen to make 2SO3 and involves the release of 198. So we can see those 2 separate scenarios there yield the overall reaction of negative 786. Okay. Let's look at another example. So I left a little bit of room here. You may not have enough to do both of the questions I want you to do. I pulled questions 28 and 29 from the textbook. So we'll take a look at this one. So again, here's the question. So with this reaction here, what's the heat involved? And then I give you 2 equations that hopefully you can manipulate to result in this. I will always give you 2 equations that are possible, that are known. We know the heat values, and we can manipulate them to get these. A lot of the times we'll see that they're enthalpy of formation equations, but we'll get into that later. Okay, so let's just start with our overall equation here. Let's look for carbon monoxide in these green equations. There it is right there. I need 2 of them. I have 2 of them. I need it to be on the left-hand side. It is on the left-hand side. So that first equation, I'm just going to leave it because it's good. The carbon monoxide matches up, so hopefully everything else will match up as well. NO, nitrogen monoxide. There it is in the second equation. I need 2 molecules. I have 2 molecules. I need for it to be on the left hand of the equation though, and it's on the right. So this second one, I'm going to have to reverse. So the first one leave alone, the second one reverse. So the first one, just rewrite it. Second one, change the reactants and products around. 2NO is now a reactant. Nitrogen and oxygen are now products. And what was endothermic, plus 180.6, is now exothermic, negative 180.6. And as you see here, we have oxygen on the left and oxygen on the right. Those can be cancelled out because you can imagine it as it's been produced in one step, used up in the next step, so it's gone. And lo and behold, we should end up with what we want. 2CO plus 2NO. 2CO2 plus N2. There it is, so we're good. And then Hess's law says that if we can add up those equations to get the overall equation, then just simply add up the enthalpies, and that'll be the enthalpy of the original question. So negative 566 and negative 180 gives us negative 746.6. Okay, let's look at 29 now. Now what I'm going to have you do is copy this out and see if you can manipulate it and do it. And then in part 2 of the video, we'll go through the answer here. So copy this out and then try it out. And then tune into the second part of the video.